Kia ora, hello, good morning again everybody. This is my second video for the lockdown. I may stop counting them shortly. In my last video, which I hope you've looked at, I established this little formula here that the force on a spring is equal to a number times the extension, the extra length, and that number is proportional to the K, the spring constant, and K is measured in newtons per meter, or K is also in newtons per meter, using that way of doing it. And I showed that up here and there, and I wanted to drop that K in there. If I move along a little bit and draw another graph of the force on a spring, the extra length, the extension, in year 13, that's also called Y. And so we can either have F is equal to Kx, F is equal to Ky, and I don't want any ribald, rude boy jokes on that one, just handle it. Interestingly enough, often there is a negative put in there, because for a spring, if I displace it this way, extra length that way, the spring pulls back with a force this way, and the force and the stretch, or the extra length, I don't know why, that's where you find that in year 13, are always pointing opposite to each other. If it's a compression spring, like a rubber bumper on a wharf, and if you squish it up a little bit like this, and it sticks out a little bit on the sides, then your extra length has gone that way, but the rubber bumper is pushing this way. So the force and the extension, or the measured of Y, are opposite to each other. Something that I haven't made a big thing about is that the work done for a system is not always equal to force times distance. Work done will be equal to force times distance if the force is constant, and that's true when we have something being dragged over a distance. What actually is the case is that the work done is equal to the area underneath this curve here. So this is a force, this is the extension, also called the Y, and that work done is equal to the area under. And for when you get to calculus, that's the integral. If we look up here, they don't have a rectangle. We've actually got an area which is a triangle, and we know how to handle triangles. I might just change a different color pen here if I can. Can we change that? Yep, cool. Oops, flick back there, sorry. The work done is equal to area, which is half times the base, and the base is the extra length. Stick with that one for now. Times the height. Well, this is the force. Times the force. And my favourite word in these, but, oh, my pen's done that again, sorry, but the force is equal to the spring constant times the extension. So the work done is equal to a half times x times kx. The work done is equal to a half K, the spring constant, times the stretch or the extra compression, the change in length, squared. And that's always positive, because if you're going to worry about the negative applies to the x, and there's two negatives in there, so you can forget about it. It's energy is always positive for the work done, and that's kind of lovely. And you can look at it in terms of being the average, if you like. It's a half, and that's pretty much where that's going to go. Now the nice thing is I'm going to stop there. I'm going to post this video, and I will then send an email out, because we're going to be, this is the last bit of mechanics. You have now been taught all of the stuff you need for the mechanics booklet. We've got work to do, but we'll stop learning new stuff now. I'll post this